All right. Good morning, everybody. Welcome to week 2 of Cisco Live Amsterdam. Oh, it's day 4. It feels like week 2 for me, I guarantee you. I'm getting too old for this. My name is Max Erdic. I'm a distinguished engineer, part of the data centers business unit. And I don't know, some of you, I know some of the faces, I've already seen them. You are used to see me presenting VXLAN multi-site, ACI multi-site, multi-pod, stuff like that. Today, it's a little bit a different session. I inherited part of it from my friend and colleague, Lucas Kratiger. So actually, that's the nice way of saying it. The other way is that he dumped the session on me, which is actually what happened. But it's OK. I'm very happy to talk about this because we are talking about multi-tier fabrics, which obviously relates a lot to building also VXLAN multi-site, ACI multi-site. And we are going to touch upon actually how the different fabric options that we offer today fit into these large-scale data center or scalable data center design options. Before we start, just before the session, another thing that I always do, which is not good, but I do it, I make changes to the presentation at the very last minute, right? So I posted the latest version of the slides, the one I'm going to present in the room, in the WebEx room. You can find them there. They're not drastically different from what you may have found on the web already, but if you want the latest version, you can download it from the WebEx room. The WebEx room will also be used for answering your question. I try to answer to learn how to answer on WebEx and present at the same time. It's kind of challenging, so I will look at the question later. But the room is also going to be open for a couple of weeks, right? 2-3 weeks. So if you have any question after, just send it there, and I promise you that I will respond to you. Okay? So in terms of agenda, I'm going to start covering some of the fundamentals of building data center fabrics. I'll go a bit fast because hopefully I'm not going to shock anybody when I talk about leaf spine, why we build leaf spines. But the whole point is to level set the conversation and then discuss how do we evolve the design from a traditional leaf spine, which now I call it traditional, right? It used to be not traditional, but traditional leaf spine topology to a more distributed architecture. Why do we want to go to a more distributed architecture? I will touch also a little bit on a controversial topic, which is building modular versus non-modular spines, right? Why should go one way or the other? I'll give you my opinion. I'll give you some food for thought. But obviously, I want to make it clear, these are options, right? We still build modular chassis. We still build non-modular chassis. So you will see what I mean when we get to that part. And then what we're going to do, as I said, I cannot escape my fate, so I need to basically map this distributed architecture to the offer that today we have, right? So we'll talk a little bit about how I build a distributed data center with ACI, and we'll talk about a little bit about multi-pod, multi-site, how I do it with VXLAN. I'll give you a couple of teasers or new information about new stuff we are working on, something that you may not have heard yet, because we are not officially talking about this at Cisco Live this year. We presented yesterday a Tech Field Day session where we talk about that, so now the cat is out of the bag, and so I decided to add a couple of slides and let you know what we're working on for the foreseeable future, okay? And then the last part will cover more building distributed data center, routed fabrics, right? So we always talk about ACI, VXLAN, VPN with overlay, and in many cases we need overlays, right? We need overlays to support legacy application. We need overlays to have a flexible way of extending layer 2 between data centers, inside the same data center. But there are also customers, there are also use cases that only requires building routed fabrics, right? So if you think about a cloud-native application, Kubernetes driven, right? You don't need an overlay for that. All you need these Kubernetes nodes to peer BGP with the fabric and leverage a single routed domain, right? So I'll touch upon that at the end and talk about these routed fabrics. And this is where most of the session is done at the architectural level. The very last part will go a little bit more in the weeds about routed fabric, and we'll talk about some of the some functionalities that we offer on our side that we have been offering actually for quite some time that you may not be aware of to simplify the deployment of routed fabrics, right? So if you are a Kubernetes app owner, right, or app developer or deployer, you may not want to be a BGP CCIE expert, right, to run a fabric. And we will see how we build some functionality into the code to simplify the deployment of these routed fabrics. So that part of the session is actually combining two original sessions into one. So it goes a little bit more in detail, and you will see some CLI as well, right? So we go from the architecture to the nitty-gritty details of the CLI. So without any further ado, paradigm and fundamentals. Leaf spine topology, we are all familiar with that, right? Now we call it differently. Some people call it the fat tree, some people folded clause, three-stage clause. Charles Claus was an engineer that, mid-50 built or proposed this topology for telecommunication network, right? Circuit switched network. But that's how most of the data center today look like, right? A leaf spine topology. When you build this leaf spine topology, you essentially have two tiers. The leaf, where you connect the entities, endpoints, services, external routers maybe, and the second tier, the spine. The spine is the backplane of the fabric, which basically allows leaf-to-leaf communication, okay? The two tiers also can be seen as three stages, right? So if I have a communication between two entities connected to different leaf, my traffic needs to go leaf to spine to leaf, right? So I have a three-stage forwarding mechanism to take traffic from one host to another host inside the same leaf spine topology. And it is a scale-out architecture in the sense that depending on my needs, if I need more ports, if I need to connect more stuff to my fabric, I can increase the number of leaf that I connect to my fabric. If I need more bandwidth, east-west, I can increase the number of spines that build the backplane of my fabric, right? So basic fundamental concept that hopefully you are very aware of. So now why do we build this fat second tier or fat spine tier? There are a couple of reasons, right? One is resiliency, right? Traditional designs, I'm talking about campus or even traditional data center design, there were two big boxes, aggregation boxes, right, deployed, where all the access layer switches were connecting to, right? Now, we put as much redundancy as we could in these big modular boxes, dual supervisor, dual power supply, et cetera, but it didn't change the fact that if something happened to one of the box, right, I was going to lose 50% of the forwarding capability of my fabric, okay? Building a fatter second tier with multiple spines ensure that when, because it's not a if, it's a when one of the spine fails, I can minimize the exposure in terms of bandwidth capability that I offer in my fabric, right? So in an example of 4 spines, I lose 1 spine, I lose 25% of the forwarding capability. If I put 8 spines, I lose 1/8, right? So you get the point. So more resiliency and less brownout exposure when something fails. The second reason, obviously, is because, especially when we talk about also Kubernetes, the cloud-native application, there is a lot of east-west connectivity requirement in the data center today. For a single flow that comes from an external user, as I always say, nobody builds data center just for east-west, right? It's not a toy. You need to provide services to external user. But for each flow that comes in, from an external user perspective, we estimate that you have at least 8 communication that happens east-west inside the data center between the different components or services of the application that is being accessed by the external user, okay? And that means I need more bandwidth. And as I said, by building a larger second tier or a wider second tier of spines, I can increase the bandwidth that I have for my east-west connectivity. Let's go on. And in terms, other two terms that comes off often is, okay, the bandwidth requirements we just took, right? The east-west bandwidth requirements and the oversubscription, right? And now, don't expect me to tell you, you need an oversubscription of 1.35 and you need 1.78, right? It's a subjective case-by-case decision, how much of a subscription you need. We will make some example, but will be just an example. I'll give you an example from a math perspective of a network built with one-to-one oversubscription, right? Depending on the application that you need to host in the data center, you need to adjust that level of oversubscription. And obviously, oversubscription needs to consider the amount of bandwidth I need between the leaf and the endpoints connected to them, and the amount of bandwidth that I build between the leaf and the spines, and obviously assuming, I said before, right, we build data center to provide access to external user. Depending where my interface to the external world is, I need to consider the bandwidth that I build between that interface, the border interface, and the external world, okay? So, how many spines do you need to build? And the answer is, it depends, right? There are two answers that you guys love. The first one is, it's on the web. The second one is, it depends. Now, I'm using the second one. It depends, because this is not on the web yet. So it will be on the web at the end of the presentation. So it depends, right? So, and I make an example, and as I said, it's just an example, so you can adjust it based on your specific requirement. I make an example of a network, leaf spine, and let's say I want to attach a bunch of rack to this leaf spine topology, where in my example I have 48 servers per rack, where each server has two 25 gig NICs, right? So for redundancy, we connect one server, obviously, to the two topo rack leaf that we have, okay? That means that if I want to have, in my example, no oversubscription between the bandwidth toward the server and the bandwidth between leaf and spine, I need basically what? I need to build 48 times 25 gig of bandwidth between each leaf and the spine, because I have 48 times 25 gig requirement downside, okay? What does 48 times 25 does? I'm bad in math, but it becomes 1.2 tera of bandwidth. And 1.2 tera, assuming in my example that you build a fabric with 100 gig interfaces, which is becoming quite common. Actually, there are people who go to 400 gig already. It will mean that each leaf requires what? 1,200 gig interfaces to connect upstream, right? Now, how many spines are required for that? Even that depends, right? Because I have 1,200 gig link that come up here. I could do 12 spines, as an example, where each link goes to a different spine. Or I could aggregate 2 or 3 or 4 links to the same spine, right? And have a smaller number of spines. In my example, I say, well, let's put 12 spines. If I put 12 spines, and 100 gig from each leaf goes to each of the 12 spine, it means that if we look a little bit at the math, with an A-slot modular chassis, I will need, with line card, 3600 gig line card, it allows me to support 288, it gives me 288 spine ports, which means I can connect down 288 leaf, right? With this principle, I can build a fabric that gives me one-to-one oversubscription with 288 leaf by putting up here a 8-slot modular chassis, right? That connects 100 gig interface down to each leaf, which allows me to build a fabric that can host 13,828 host port, whatever it is, right? Again, with one-to-one oversubscription. If you change the oversubscription, you will get, or if you reduce the number of leaf, you can play with these numbers, right? It's just an example. Now, the question comes, what happens when I need to connect the host 13,829? In a technical term that they use in America, you are SOL. I'm not going to spell it for you because I'm recorded. You go Google it. But you are SOL because you use all the interfaces you had available on your spines. Your fabric has been exhausted in terms of interfaces available, right? So what can I do? Well, one thing that for sure you will love to do, you replace the modular chassis A slot with a bigger one, right? It's like the movie Jaws when he says, Errol Flynn says, we need a bigger boat. Here we need a bigger chassis, okay? So you go from 8 to 16, which you will love to unscrew these, unplug the interfaces, plug it back, right? But if you do that, well, you see the math, you can basically double the number of spine ports you have. So you double the number of leaf you can connect. You double the number of endpoints that you can connect to your fabric without changing the oversubscription, which was your criteria to build this network. Okay? The other option you have, I change the speed. I don't change the size of the chassis, I change the size of the interface, if you want, connecting the spine to my leaf. So I move from 100 gig interfaces to 400 gig interfaces, right? And so I still use an 8-slot modular chassis, but now instead of 36 times 100 gig line card, I put 36 times 400 gig line card, which means I need to replace all the line card, I need to reconnect all the links, and yada, yada, yada. That gives me even more ports, right? 152 spine ports using obviously breakout cable because this leaf, remember, were 100 gig up, so you don't want to have to change all the leaf. You can use breakout cable from the spine to convert each 400 gig interface to 4 100 gig and connect up to 1152 spine ports, right? So I'm building a quite big fabric with that, right? But doesn't change the fact that if one day your business thrives and you need to connect the host to 55,297, you're back to the same problem, right? So you basically building a leaf spine topology, it's very linear, or in general, a two-tier network is a very linear in terms of scale or what you can achieve, right? And these are the two examples I made, right? You can increase the scale in one way or the other. It's a scale-up approach, which is not bad, but eventually may still get you to the roof, where you cannot grow anymore, okay? So what can we do about that? The other thing we need to think is that I talk about 16-slot chassis or 8-slot chassis, right? That's the status quo. That's what you are used to build in the data center, right? The aggregation layer, the distribution layer, it's a modular chassis. It was almost dogmatic, right? But as you know better than me, ASIC improvement during the years now allow us to build boxes, 1 rack unit or 2 rack units that provides more bandwidth availability than a 16-slot chassis, right? So what we can do is try to evolve the design to follow the evolution that we had in the ASIC space. And the design evolution is actually two aspects. The first one is changing the status quo or the mindset of, okay, my aggregation, my distribution layer needs to be a modular, because that's what I always did, and start looking into a non-modular one. And second step, and we'll talk a little bit about some consideration about modular versus non-modular. The second step, instead of continue to make my leaf spine topology bigger and bigger by adding leaf nodes and so having to increase the capability of my spine tier, I go to a more distributed architecture, right? And we will see what are the benefits of doing that. So, why adopting non-modular spines? And here I know we are entering the controversial territory. I don't want to, push anyone one direction or the other. We are not getting out of the business of modular switches, to be clear. We still have, in the data center at least, right? 9500 Nexus is still there, alive and kicking. We have invested into, our new ASIC Silicon One. We have a new 9800, 9808 that is available, 9804 as well. So it's not that we are removing the producing modular chassis. Here is some points to chew on to try to understand, does it still make sense for me, or for you, I would say, to build or to buy and build a network based on modular chassis or not, okay? And the first thing to consider is, I show you this topology at the beginning, and I said, well, when you build this, you build a two-tier network, we all agree, leaf and spine, and it's a three-stage network, because when I want to have a communication between endpoints connected to two leaf, I go leaf, spine, leaf. Well, in reality, if I zoom in, when the spine is a modular chassis, and I go to zoom in, this is what happened. Each of these spines, what essentially becomes, it becomes a mini leaf spine fabric, right? Why? Because inside the modular chassis, each spine has line card, it has fabric modules, and every time I have a communication between one interface of one line card and one interface on the other line card, the traffic will go line card, fabric module, exit line card, and then down. So my three stages fabric that I thought I built now becomes a 5 stages, right? Leaf, spine, 3 stages inside the spine, exit leaf. Why do you care? Well, you may not care, and it's fair, but when we go and talk about latency, right, that essentially means that the latency that you will experience, depending where you connect stuff in your data center, may vary. And you may see, instead of a 3 microsecond latency that you have in a true 3-stage fabric, you may start experiencing 5 microsecond latency, because you have the latency due to the architecture of the modular chassis. Okay? The other consideration is that most of the modular chassis normally works in store and forward mode and not in cut-through, which also has an implication on the latency that you experience, right? So again, depending what application you need to host in the data center, you may care, you may not care. But if you care, it's something that you need to be aware of, that sometimes remains a little bit hidden behind the curtain, right? The other consideration is operational, right? When you build this network, this fabric, and you operate them, what do you do? Well, you are master of routing protocols, right? So you usually have your OSPF or BGP running between leaf and spine. Depends, obviously, we'll talk a little bit of the type of network you're building. It's a fabric with overlays, non-overlays. You know how to enable BFD if you want to avoid problem of a unidirectional link or link that stays up and don't forward anymore. You are a master of everything that happens between the leaf and the spine. But what about inside? If something doesn't work inside the chassis, what do? Can you go inside and see, oh, let me go to the line card, do show IP route, and see if I see the route from the exit line card? You can't, right? I'm not saying that we kept you in the dark. We developed, because I have colleagues that the first time I presented this were like, oh, but we did a lot of work to give visibility inside the chassis, what's going on. Absolutely. But it's a more obscure way of looking at the operational aspect of what's going on, right? When something doesn't work, troubleshoot why that traffic flow doesn't go through, right? And you cannot definitely reuse the same know-how that you already have based on protocols that you have been running for maybe 20 years of your lives, right? So there is this operational aspect as well. And I'm not saying that modular chassis are bad or they're faulty. They're very robust and resilient. But things happen, right? And sometimes something may stop working, and this is where maybe you call my friend Ramses attack, and he come and help you, but you cannot use the tools that you're used to normally, okay? There is also another consideration, and we'll talk about that in a second, right? Here, I try to collect some pros and cons of modular versus non-modular. Again, could be a controversial slide. And again, I'm recorded. I'm not saying you should not deploy this anymore. I just give you some food for thought about things that you may want to consider before you make your choice, okay? One other aspect is the power, right? So as I told you before, now with non-modular chassis, they look a lot like top of rack, right? They are 1 rack unit, 2 rack unit spine, whereas before was a 16 rack unit spine. What does it mean? It means from a power distribution perspective, in your data center, you may have rack with 2 top-of-rack switches and rack with 2 spines that requires more or less the same power, and they look more or less the same, right? You don't have any more a need to power an end or row pair of aggregation or distribution switches that are bigger, they are modular, and they draw more power, and they require more cooling, right? All the racks are a little bit more homogeneous, which means I'm also more flexible on where I deploy, where I connect these devices, okay? That's for the part of some consideration, modular versus non-modular. What about the design evolution? Why should I look into building a distributed architecture? Why, on top of that, because you may say, well, the fabrics you showed me before was very big. It's bigger than what I will never need. So I put a 16-slot chassis in my spines, and I can accommodate my growth for the foreseeable future, right? But there are other considerations which are not really related only to the scale. Why is not a good idea to build a single logical fabric leaf spine topology, right? And these are mostly due to failure domains, right? You want to be able to build an architecture where, especially when you build overlay, because you need to extend layer 2, you want to have a control on how you extend your layer 2 across different points of your architecture, of your infrastructure. You don't want to build a tunnel end-to-end that floods everything everywhere without you having any control, right? And we'll talk a little bit about that when we look at the topology for ACI multi-site or VXLAN multi-site, for example. Other point is when you need to make a change, or when you need to upgrade your fabric. First of all, if it's a single leaf spine topology, most likely, if you talk to Cisco, you talk to TAC, they want you to run the same code everywhere, right? On all the leaf, on all the spines, because they don't want to have mixed environment where things look different in the same fabric, in the same leaf spine topology. Second point, when you want to go and make a change, and you need to ask application owner permission to make a change, if that change is done in a single logical fabric, how many application owner you need to ask? Everybody who hosts application inside the fabric, right? What are the chances that you find agreement to give you a maintenance window to make the change? It becomes very slim, right? It becomes very hard to put all of them in agreement. Yes, let's go make the change. If you can divide or separate the deployment of application in different blocks in a distributed architecture, then it's going to be much easier to make a change in block 1 because I affect only the applications that run in that block 1 and not the one that run in block 2, 3, and 4. Okay? So there is also the aspect of how do I upgrade, how do I minimize the downtime, and how do I ensure that I can get a maintenance window to make the job that I need to do. Okay? So bigger is not always better. That's the point, right? We could argue, but so the idea is, I want to move you from a traditional 2-tier leaf spine topology to a more distributed architecture, okay? And how this distributed architecture looks like and how it works, we'll see it in a second, making another example, a similar example to the one I made before. And before I go there, this is nothing new that I'm telling you, right? This is how hyperscaler, or what Lucas called them, the cloud titans, have built networks and data center networks for years. There are actually papers, if you go and search, that build topology that look like the one I'm going to show you in a couple of slides. Okay, so it's nothing new. When these cloud titans with these hyperscaler built fabrics, they have 4 principles that they follow. First is simplicity. It needs to be simple to provision this network, to build this network, to operate this network. And the more repeatable you make the deployment, the easier and simpler operating them and provisioning them becomes. They need to be scalable, right? I don't want to hit the roof and say, oh, I need to add another host, but I cannot add a leaf because I'm out of port on my spines, right? That's the point we made at the beginning. So scale should never be finite, right? I should be able to scale as I go. And on the other side, I don't even want to build a network that maybe is 20% or 40% underutilized at the beginning because I just need to plan for future growth, right? I don't want to spend money if I don't need that level of connectivity. I want to be able to scale and pay as I go, okay? 3, I already touched upon that. You want to be able to handle failure, which will happen, failure at the link level, failure at the node level, but ensure that that failure is minimized and it's contained in one part of the network. A failure on a leaf here should not have any effect on the leaf on the other side of the network or the other side of the fabric or of the data center, okay? And 4, which is similar, it's basically similar to 1, I want to build a cookie cutter design. I want to build a scalable and repeatable infrastructure so that when I need to grow, I know exactly what to do. I have all my automation built, and boom, I add another block in no time, okay, without having to relearn anything. Okay? These are the 4 principles that these cloud titans have followed from the very beginning. And so let's make an example, right? The example we are making is I start building a fabric, and I said, I build a fabric with 128 leaf. Is this written in the stone, 128? It's a decision for this example. If you say, this is based on you, how big you need your building block at the beginning, how much, the consideration about full domain, change maintenance windows, how big you want to make your basic building block of the infrastructure, you'll make your decision. In this example, I say 128 leaf. 128 leaf gives me 6,144 ports, which is already a good size leaf spine topology. Now, the key point here is what I say here, right? So I put a fixed switch at the spine, and more importantly, and I make an example here, right? Just to make an example, I had 9364D GX2B to go into the specific of hardware options. It's a 64-port, 400 gig switch, right? So 2 rack unit gives you 64 times 400 gig of bandwidth, right? This goes back to my point of how the evolution of ASICs allow us to compact the size of these devices. And the goal here, the first design principle is, whatever I do, I want to ensure that assuming you want one-to-one over subscription, because I continue the example I started before, I want to keep 50% of the interfaces of the spine free. So 50% are used, so 32 ports, so 400 gig, are used to connect down to the spine. The other 32, I keep them open to be able then to connect up, if and when needed, okay? Now, if I do that, by the way, here we show there are other options. This is just one option that I show you in terms of hardware. We have other options of, no modular chassis, and more are actually coming that are not even listed here. When I exhaust the number of hosts that are connected in this block, instead of being stuck and say, what do I do? Well, I can add a second block. Right? And now, obviously, a third, a fourth, depending when, how your business hopefully grows and thrives. Now, obviously, I cannot add a block like this, because if I did like that, we're like, oh, well, how does an endpoint here communicate with an endpoint here, right? The moment I add the second block, I need to add also a third tier now. So my network becomes more distributed because I have a 2-tier leaf spine block or set of blocks that are interconnected toward a third tier, okay? And that third tier, you can call it the core, you can call it, we will see depending on which architecture you deploy. Sometimes we love acronyms at Cisco, right? We like to change them also so that you're always like, ooh, this is new. IPN, ISN, core, L3, you look at the slides, you are like, you can build, you have 100 different ways of calling this network up here. Whatever you want to call it, it's the layer, is the tier that interconnect all your different small leaf spine block, okay? And the other interesting thing, the idea here, which again, we didn't invent, Lucas didn't invent it, yeah, I didn't invent it, is we build what we call it as planes. Planes means each plane is a color, right? That's how, again, hyperscaler built massively scalable data center for years. Each spine in the block, in each block, as a color and connects to the core device of the same color. The second spine is a different color, connects to a second core device, right? Why do I want to do that? Two values. The first one is, whenever I want to have a communication between an endpoint in Fabric 1 and an endpoint in Fabric 2, for example, the first decision is made at the source leaf. The source leaf most likely will have an ECMP decision to do, right? To get to that destination, I can go through 4 paths in this example that take me to spine 1, 2, 3, or 4. Once the first decision is done and I decide which spine I want to go, I'm going to stay with that lane or with that color end to end, right? If I pick blue, then I'm going to go to the blue core, and then I'm going to go to the blue spine in the destination site, right? If I pick green, I'm going to go green, and I'm going to go green all the way to the destination. So it's much easier to follow based on the decision that is made by the leaf, by the ingress leaf. It's much easier to troubleshoot and follow where my flow is actually going across the infrastructure, okay? The second value is I control better the amount of bandwidth, the oversubscription that I build between the blocks, right? So in this example, I have 400 gig links that I use, because if you do the math, that's what I need to basically have a one-to-one oversubscription between the bottom and the top. So I could say I use 400 gig port to connect each spine, right, to the core. If I need more bandwidth, I can increase, you maybe haven't seen it, but if I do this, you see it. I can increase the number of ports. I can say instead of having one 400 gig going to each lane, I do 400 gig link to go to each lane, right? So I increase the bandwidth I have between each spine and its core lane, and based on that, I increase the bandwidth available between each block and the external network. I can also do something more crazy, which is, if I still want to support a large number of fabric, because obviously the moment I use more links going to the same core box, depending on the choice I make on this core box, it affects how many building blocks I can build overall, right? If I want to keep the maximum possible number of fabrics that are part of the same architecture, I could add, instead of increasing the number of links to the same core, I can add more cores, but still maintaining that different plane separation: blue, green, red, yellow. Okay? So you have choices that you can make to determine how you increase or decrease the bandwidth, depending on the oversubscription factor, oh my lord, that you want to achieve. Okay? And these are examples, right? But it gives an idea of how you build this distributed architecture, and now you can control the bandwidth in a more precise way, right? Now, let's consider this topology as the basic topology going forward, right? And now let's see if we agree or not agree, but me and Lucas agree, if we agree that this is the right, and the hyperscaler agree as well, this is the right way to build a scalable data center, right? And again, doesn't mean you need all these blocks from the beginning, you start with one, right? How does this map to the different architectural options that we offer you, right? And here really depends on which camp you are. Are you an ACI customer? Are you a VXLAN VPN customer? Are you a customer that doesn't require overlay and needs to build routed fabrics? The beauty is, whatever choice you make, it doesn't change the fundamental principle of the architecture that you need to build, of the distributed architecture you need to build. But just for my own knowledge, how many of you deployed ACI? Okay, how many VXLAN VPN? Purely routed? So it's like 40, 40, 20, at least the one that raised their hand, right? So it's a mixed environment, right? And this is where I will show you also something new when I will touch upon this concept here, the concept of heterogeneous fabrics, okay? So quickly, and this is probably just a recap, or, but how do ACI fabrics or the ACI architecture map to that distributed data center design that we saw 2 slides back? Well, one thing I could do, I could use something that we call ACI multipod. Right? ACI multipod means I built n of these blocks. These blocks are not fabric, they're called pod. Why? Because they're all under the control of the same epic controller. Right? Multipod is a distributed single logical fabric. As I always say, multipod is very easy to provision, is very easy to operate, is very feature rich because everything that works with a single pod ACI fabric works with a multipod ACI fabrics because we don't introduce any new controller, we don't introduce anything new. It's just having the same epic, the same brain controlling more pods at the same time. And the scale that you can achieve with that, we can go today up to 25 pods, part of the same fabric, with a maximum number of 500 leaf, right, across. So obviously you cannot do 128, 128, 128 times 25 because the maximum number of leaf that we tell you can build in a single multipod fabric is 500. And these are scale number, and frankly, even if you could build more than 500 leaf switch under the control of the same epic controller cluster, I don't think you should, right? 500 is already is already putting a lot of eggs in the same basket, because as you know, when you build multipod, all these pods are steady state and need to run the same code, right? So you have more dependencies between each block than you have, for example, with a different option that we're gonna see next. Okay, makes sense? So multipod makes sense, but makes sense depending on the use case that you have. The other side of the spectrum with ACI is doing multi-site. Topology doesn't change, remains the same. But now, each of these blocks becomes a fabric. Becomes a fabric with its own epic domain. So we go more toward the concept of separating the failure domain, giving control on how I establish connectivity between them, because not everything is stretched. Layer 2, if I define a bridge domain here, I may say that bridge domain is only local to this site. I don't need any layer 2 extension, right? With multipod, everything is extended by design. It's a single fabric. With multi-site, you have tight control, what you extend. Layer 2, what you extend, layer 3. Each of these is a different epic controller. Each of these can run a different software release. Each of these can be upgraded independently, right? That goes back to the point of only the application that run in Fabric 1 are affected when I go and do the upgrade to that block. Nothing needs to be considered for Fabric 2, 3, and 4. Okay? And here I put all the links. I presented the session. Some of you maybe were there, right? Also the previous one, John Weston presented the multipod session as well. So you have also, if you're not familiar with this architecture, you can go and dig a little bit more. There is the hybrid case as well that I wanted to mention it because it's always, when they ask me multipod or multi-site, the answer is always both, right? Because actually you can build a fabric with multiple pods and interconnect multi-pod fabrics with the orchestrator, right? With multi-site. So this gives you a mix of advantages of disadvantages, the previous two options, right? Because I have less fabrics to manage independently. I have areas where I build logical fabrics that are the pods that are part of the same epic controller cluster, but I still maintain a separation between different multipod fabrics. So you can choose also to go down the path. Again, nothing changes in terms of how the infrastructure looks like. What about VXLAN and VPN? If you're not ACI, the other 40% that said no ACI, well, we have an architecture. Here is a little bit simpler, right? Since I show this guy here, and I will touch upon that in a second, but with VXLAN and VPN, we do not mandate that a controller is deployed together with the fabric, with the network, right? In ACI, there is no ACI fabric or pod without the epic. In VXLAN and VPN, it's an option to have a controller or network manager or whatever you want to call it, but you could deploy a VXLAN VPN fabric or multi-fabric environment through CLI, through Ansible, through Terraform, whatever you want, right? You could build your own controller, homegrown controller. And in terms of architecture and technology, actually I would say architecture, here we don't have a distinction between multi-pod, multi-site. The message is very clear. They're very fast in the other room. I mean, is it me that is low? Or, okay. VXLAN multi-site or multi-fabric, whatever you want to call it, is the architecture that we always recommend for every deployment. Why? Because we have this layer here, which is called the border gateway, which is that piece, that component that allow you to control connectivity between the different blocks, right? I allow you to control, do I want to extend layer 2? Do I want to extend layer 3? Do I want to keep a subnet limited to one site? Do I want to keep flooding limited to one fabric? Or do I want the flooding, allow flooding across? And how much flooding traffic should go across, right? So that border gateway function, it's a key component that should always be part of a multi-fabric VXLAN VPN architecture. You could build these without border gateway and just do a single logical fabric divided like this with VXLAN VPN, but it would make little sense because you want to have the level of control that the border gateway provides, right? That's why we removed, I worked on a VXLAN multi-pod paper 10 years ago. We remove everything from the internet. Some people still have it saved on their hard disk, I'm sure. And now the only architecture that we really recommend is using VXLAN multi-site and leverage border gateways to interconnect these different blocks, okay? And the border gateway can be on the spine, as you see here. So it remains a two-tier leaf and spine, leaf or border spine, as we call it, border gateway spine topology for each block, okay? Let me go back 1 second. If you don't want to operate this, provision it through CLI, NDFC has become a very good option, right? And I would never imagine to be on a stage saying that in the times of old DCNM, right? DCNM was not a great product, I'll be honest, right? NDFC compared to the old DCNM is day and night, right? Completely different, or night and day, I should say. So what you could do, you could build a single NDFC service instance that, as you know, based on ND runs on Nexus dashboard, and you could use this to manage a certain number of these fabrics, right? Depending on the version of NDFC that you run, you can look at the scalability guide or the release note and tells you how many fabric can be managed by the same NDFC instance. But the important point is that you can have a single NDFC instance managing multiple of these blocks. The architecture, the technology, the use of border gateway, the use of border gateway with standard BGP VPN between them remains exactly the same. It's just a provisioning and troubleshooting tool that you get, okay? The other option is saying, I do an architecture that mimic the ACI multi-site. So I build different NDFC domain because I want the separation also at the management layer, where each NDFC domain manages a subset of these fabrics. And then I use the orchestrator to orchestrate the connectivity between the fabrics that are managed by the different NDFC instances. We did this to have a consistent architecture between ACI and standalone meaning VXLAN VPN. Now, that said, unless you are running this, if you're running this today, I put this slide because I wanted you to feel good that, yes, it's still a viable option that we stand behind. If you are looking into starting today with a multi-NDFC instance deployment, this should not be the way to go, right? Why? And I'll be very blunt and clear with you. NDO was built from the beginning to work with ACI. Then we extended it to work with VXLAN VPN, but has always been in catch-up mode, right? Features that were working with ACI fabrics, not working with VXLAN VPN fabric, roadmap ask. So we got to the point where we were like, you know what? We are going to keep NDO. We're going to keep NDO for ACI, multi-site, and we're going to work, it will be faster and easier to work on a different approach when I need multiple NDFC instances to work together. And this is the first teaser. This is the first new thing that I'm mentioning. Is something that will be called One Manage. And what one managed is something, I say future is this calendar year, more or less, which, calendar year 24. What one managed means is that I will be able to federate different NDFC instances so that do not require a separate orchestrator to talk to them, but there will be more a master-slave type of relationship between these instances, right? So I will be able to control the configuration of the border gateways of all the fabric from a master. Obviously, if the master fails, a slave instance will take over. And that means, it gives you the benefit that if you're used to run NDFC and to manage NDFC, you don't need to learn a new tool, which is NDO. If you use the API of NDFC, you don't need to use API of NDO, right? It's more consistent with the way that you may have been using NDFC already, right? So these, if you need to start with multiple NDFC domain, I would say today, wait a second, right? Stay maybe with one, which is this model here. And then we will give you a migration. If you want to separate a single NDFC domain into two or more using one manage, there will be a migration procedure to ensure that fabrics that were managed by one NDFC can be passed, if you want, to another NDFC instance. Okay, but this is where we want to take you if you like NDFC and if you want to use separate NDFC domain to manage your distributed fabrics. Does this make sense? Did you know about this? See, if you knew, it's because you went to the Whisper suite or you are very well connected, because we haven't talked too much about this up to now, okay? The second teaser, and I have only one slide, is about heterogeneous fabrics. So what we cover so far when we talk about ACI fabrics or VXLAN VPN fabrics were very homogeneous deployment, right? So I interconnect with multi-pod or multi-site different ACI leaf spine topology, or I interconnect with VXLAN multi-site different VXLAN VPN fabrics. We have customers that for years have asked us, well, we actually have both, right? For different reasons, we built different fabrics. So there are some customers that have both, and they're like, how can we interconnect these two domains? And the answer has always been, well, you route through them, you connect them to the backbone through what we call the L3 out, right, in ACI and VXLAN and VPN, and you just route between these fabrics, which is totally, in many cases, is fine. But in some cases, the use case is, well, I have a fabric of one type, I want to build another fabric of a different type, and I want to be sure to extend connectivity between them as if they were homogeneous, right? I want to extend layer 2. I don't want to have to deploy an external L2 solution or L2 extension solution, because the architecture does not allow me to interconnect heterogeneous fabric, which is the reason why we work into creating, and this is in the work and it will come in a few months, what we call it an ACI border gateway, right? And I see people take pictures like, yeah, this is new. Well, ACI border gateway, the purpose is opening up connectivity, L2 and L3, for now I'll just stay at the connectivity, between ACI and VXLAN and VPN fabrics, right? They all become equal class citizen. Doesn't matter of the specific technology you have in each of these building blocks, because they're all interface with each other using this border gateway layer or tier. And this is a border gateway that speaks standard VXLAN and VPN, right? And PBGP VPN, VXLAN, not IVXLAN that we use inside the fabric, is just regular VXLAN. And by configuring, the border gateway is obviously on the VXLAN side and on the ACI side, I will be able to control how I extend layer 2 and layer 3 connectivity, if I want, between them, right? So now you see the architecture start becoming consistent, right? It doesn't matter anymore the type of fabric I have. If tomorrow we come with, or you have a vendor that comes with another fabric option, as long as I can have my border gateway layer there, that block can be connected to the multi-fabric environment, okay? If you have a campus network running VXLAN and VPN, and actually we support it today also with NDFC, we can put Nexus 9000 border gateway connected to the campus VXLAN and VPN network and extend layer 2 and or layer 3 connectivity to the data center, right? Managing everything to the same NDFC pane of glass, right? Here I show single point of management. What this single point of management is, you don't care. It will be obviously Nexus dashboard, will be functionality running on Nexus dashboard. The fact that it's called NDO, NDI, NDP, or NDC doesn't matter. And actually what we're doing on Nexus dashboard, we are trying to remove the differentiation of the naming of the services. We want to give you on Nexus dashboard the functionalities, right? Functionalities for provisioning, functionalities for troubleshooting. We don't care if this functionality are to provision a VXLAN VPN fabric or an ACI fabric. Will be a common look and feel, right? And so that's why you see these that will allow you to provision, talk to Epic, talk to the switches up here, and provision everything you need to do. Does this make sense to you? Would this help some of your use cases? Does it make you feel, because sometimes people were like, oh, went ACI, I feel trapped because ACI is a closed system. ACI is not a closed system, has never been, but now even less. Right? I can connect my ACI fabric to a VXLAN standard VPN fabric without any problem. Right? And this will come mid of this year, the first instantiation. Toward the end of the year, we will fill all the functional needs that are required. Okay? We'll work with multi-pod or multi-site in each site. Okay? I need to drink. Give me 1 second. You're very quiet. I don't know if you're very quiet because you are shocked or you are tired. I mean, I understand. Yesterday was it the party last night? No. No party? Oh my God. What happened? Huh? It's tonight. So there is no excuse about being hangover from the party. So come on, guys. All right. See, as soon as I say that comes a question. It's like, oh, I feel bad. Okay. And I will never hear you, my friend, not even in 100 years. Can the single pane of management be used for to provision? EMS, fault management and provision management. That's the plan. Yes, yes. Element manager you're talking about, right? As an element manager, that's the plan. Yes. And again, I put it there. I'm not saying that we have all the single point of management function already in place, but that's the direction, right? That's what we want to deliver. Okay. Now I have 32 minutes. Let's talk a little bit about routed fabrics. And my friend Lucas loves RFCs, right? If you have a conversation with him, he loves to tell you RFC names. Maybe you will never be able to say, like I am not, if it's right or wrong when it gives you a number, but it's always RFC 79, 83, 89, whatever. But here there are really two RFCs, two standards that we leverage when we talk about deploying routed fabric. And these is nothing new, right? And what I'm going to show you is how actually you leverage functionality of this RFC and you combine it with this RFC to build more easily provisionable routed fabrics. This is for the use case where you don't need overlays, right? Which are there. We have customers that don't need overlay, especially when we talk about hosting cloud native application, Kubernetes, stuff like that. So first of all, what it is RFC 5549? I said, this is nothing new. Well, look, industry-wide adoption for more than 10 years, right? And it was invented and authored by Cisco, right? I'm not saying that to blow my horn or our horn, but it's something that we did more than 10 years ago. Actually, this guy who did it here, I know it personally because he lives in south of France, where I live, right? I cannot talk to him because I don't speak French, but I know him. What is RFC 5549 for? Well, the goal of RFC 5549 is to be able to, I'm missing, no, where is it? Yeah. It's basically to be able to allow advertisement of IPv4 prefixes between network, between different BGP autonomous system using an IPv6 connectivity, right? An IPv6 peering only between switch 1 and switch 2. So in this example, right, I have a V4 network here, I establish a peering, a BGP peering using the IPv6 address that you see here, very long number, right? And as a result, we exchange, if I go to the switch 1, I will learn the subnet, the IPv4 subnet that exists in Site 2, into Site 1 with the next hop, which is the IPv6 global address of this switch 2, right? What the value is on that? Well, first question is, can I use it also if here I had a dual stack, also IPv6 inside the data center? Absolutely, right? That's why we have IPv4 and IPv6 address family. It's still a single peering, IPv6 peering, but allows you to exchange v4 and v6 prefixes. What is the value? Well, to understand the value, or to begin to understand the value, you compare the dual stack deployment that you see on the left. So I have, two networks that are dual stack, v4 and v6. And this is becoming, as Lucas always jokes, we thought we would retire before actually we saw v6 really becoming, deployed massively. But there are lots of governments that start enforcing now, or they will soon enforce, the use of IPv6 inside the data center, right? So it looks like I need to start learning it, even if I always stayed away, right? Because it is becoming real, more real. So if I have a dual stack, I have v4 and v6, because obviously not everything will become v6 from the beginning, normally I will have to do double peering. I will have to give double addressing to the interfaces. I will have to peer v4, I will have to peer v6 to exchange the two types of reachability information. With this RFC 5549, I still do a single peering, v6, with this global address, and that will allow me to exchange both the v4 and the v6 prefixes, which is actually simpler from an operational perspective because I configure one neighbor, one peering instead of two, and it also uses less memory because it's one peering instead of two, right? Less CPU power, etc. Okay? There is more to it, right? If I look here again at the dual stack, I need to configure the interface on each site with an IPv6 address and an IPv4 address. And then I create my neighbors. I create a neighbor, a v4 neighbor, and I create a v6 neighbor, right? That's a traditional way of doing things. If I compare with what 5549 allows you to do, I create a single interface, right? Which is what I said, with an IPv6 address, and I create a single neighbor. That's the immediate advantage. One peering versus two is reiterating what I showed you in the previous slide. But we can do more. We can do what we call unnumbered peering. So if you know a little bit v6, I know just a little bit, very, very, very little. But every v6 interface always have a LLA, a link layer, a link local, sorry, my lord, address, right? Which you don't need to configure, it's just there, right? So now RFC 5549 suggests that you use actually that link local address to peer with the neighbor device, without having, which allows essentially the v6 peering to come up without having to configure anything, right? So what all I do at the interface level, I say IPv6 link local use BIA, burn in address. And from a neighbor perspective, I don't need to know, you are my neighbor, what is your address? I just say you are my neighbor. Neighbor out of Ethernet 1.1. And by the way, we can do that also neighbor a bunch of different interfaces arranged, right? So that means I become neighbor using the link local address with the device that is connected on the other side of the link, right? So now you start seeing the simplification that comes in, right? It removes the need to know, to give an address to my local interface and also to give an address to the neighbor I connect to. An additional simplification. And again, this is nothing new, right? It's been there for 10 years, okay? So for the rest of the presentation, this is the starting point, right? We are using 5549 to basically simplify drastically this configuration. And again, it could be used even if I still am v4 only in the data center, right? I use this configuration just to simplify the peering. It doesn't matter if I have v6 deployed or not. Maybe most of you don't yet, and still could start benefit from this. Now, how does this fit in the data center, right? Everything we have been discussing so far. If I put this picture, right, you now are familiar with this picture, right? You have seen it in all different sources. Now this is a purely routed fabric, right? The Topology remains exactly the same, but now I use BGP, eBGP specifically, to peer spine to the core layer that I introduced, right, before, spine to leaf, and also leaf to host, right? Why? Because especially when you deploy Kubernetes, right, these Kubernetes nodes peer BGP with the fabric. Now I have a BGP connectivity basically hop by hop, end to end. And so at that point, having a way to simplify the provisioning of that connectivity, right, it's a big value add for the guys who need to manage this environment, right, this Kubernetes environment, and they just want a network to allow connectivity, kube node 1 to kube node 2, okay? And so this allows to reduce the number of control plane, data plane peering that we need inside our data center, okay? Now, what is the other RFC 7938? And this is, I want to cover this a little bit because in the last 10 years, probably even more, you had no idea how many times I had to fight or talk to customers that were like, oh, we want to build a VXLAN VPN fabric, we want to use eBGP as underlay protocol. And our question is always, and we always ask, why? Well, because that's how the vendor X told us, that's how you build scalable network, you need eBGP in the underlay, which is absolutely true. It's what RFC 7938 covers, right? The use of eBGP to build this scalable data center. But RFC 7938 doesn't have any mention of overlay. 7938 is being created for purely routed fabric, right? Actually, there is some mention of Trill. Here I show a little bit my age, because Trill, we did the fabric path version, which was a Cisco version. Trill was like for layer 2, right? It was a way to build layer 2 fabric, right? Fabric path Trill. But there is no mention at all of overlay, right? So 7938, you can think, yes, is still relevant. It's a bit dated because it doesn't have reference to IPv6. It doesn't have reference to 4-byte ASN, which many people start using in terms of BGP. But it is still something that drives you how you build this scalable, how you deploy this scalable routed fabric, right? Has nothing to do with overlay, okay? But since here we're talking about routed fabric, the goal is how do we marry the principle that 7938 gives you with some of the advantages of the other RFC in terms of easing the provisioning of this BGP peering. And this is where we came with something that we call BGP Auto Fabric. BGP Auto Fabric is available from NXOS, I believe, 10.2.3. It's only available for standalone. But here we're talking about routed fabric, so we're talking standalone. We're not talking ACI or VXLAN VPN. So in NXOS 10.2.3, I think, is the first release. Now we are at 10.4.2, right? So we have additional functionality available. What BGP Auto Fabric is, it basically allows me to build what we call it as a... First of all, is any of you aware of BGP Auto Fabric? We did a great marketing job. Look at that. Richard, take note. 0 person know about BGP Auto Fabric. Okay, so this is the beauty of our marketing organization. Okay, what is BGP Auto Fabric? Allows you to build self-organized BGP fabric. What does it mean? I want to be able to build the topology I showed you before without having to worry about what is my BGP autonomous system, what is the neighbor autonomous system, what is my interface, your interface. I want just a plug-and-play environment where I can bring my fabric up together, my distributed fabric in our case up together, and then start connecting my application without having to worry about knowing too much about what's going on. For the provisioning, obviously I want to be able to see what happens, and I will show you a CLI. This is where we go a little bit more in the detail now. I'll show the CLI how you see actually what has been provisioned, if you need to. But if you don't need to, the fabric will just come up and be ready for consumption, okay? And this is basically to deal with the leaf to spine, and in our example, the spine to core connectivity. Then there is the other part, which is the connectivity between leaf and, for example, the Kubernetes nodes, because differently than traditional application that usually were connected layer 2, right? These peer also layer 3 with the fabric. I know that mainframe already in the past were used to peer layer 3 or SPF, but even more now, right? And we have a couple of papers actually that talk about how you deploy Kubernetes with our fabrics, right? And also with our router networks. But this, basically what BGP Auto Fabric brings to the picture is the capability of bringing together the end-to-end story, right? I want to be able to, I'm a Kubernetes administrator, I want to be able to connect my Kube node to the fabric, and I want my fabric to just do what it has to do. I don't care about any BGP, I just want it to route, okay? So, how does it work? Take a simple topology. I don't do the old distributor, let's look at the leaf spine and let's magnify spine 1, spine 2, and leaf 6. Okay, I have these three interfaces, they're connected like this. This is how the configuration will look like on the three nodes to basically establish my BGP peering. Router BGP auto. I don't care about my BGP autonomous system, I just say auto. How is this box determining what this auto means? Is based on the system MAC of the switch. Right now, all this is supported only on Nexus 9000 switches right now. So I'm pretty confident that the auto value that spine 1 picks is different from the auto value that spine 2 picks. Right? So every node in the fabric will have a different BGP ASN, which is actually important, just as a side note, because if you think about leaf, spine, leaf, if you deployed eBGP between leaf, spine, and leaf, and the two leaf were part of the same autonomous system, by default, would you be able to exchange prefixes between them through the spine? Who says yes? So everybody say no. Why not? Because if the source of the originate the prefixes in an autonomous system 1 and the receiver leaf is in the same autonomous system 1, guess what? BGP has a check on the S path and will drop the prefix, right? So now you need to start, if you do that, you need to start tuning settings at the spine. You need to ensure that the same prefix can actually be received and imported on the destination leaf, even if it's coming from my same autonomous system, which may break or endanger some of the loop avoidance mechanism of BGP, right? So this basically ensures that each node will have its own autonomous system, BGP autonomous system, based on the system MAC, which is unique per box, okay? Second thing, router ID that I use to peer is also auto. Again, same story, determined based on the system MAC. And then what I already show you, the interface use the link local address and neighbor Ethernet. So I configure the BGP neighbor based on the interface I want the neighbor to be on. And remote AS, I just say external. I don't need to know what is your remote AS. I just say it's an external BGP because I know it's external because each node has its own autonomous system derived. You see this configuration? This configuration pretty much cut and paste on all the nodes will allow all your BGP peering to come up without having added a single number into the configuration, right? That's the value of BGP Auto. And here, if you are a little bit geeky, this is where then you will see how this configuration, what will reflect in terms of the ASN that is provision, the local, the remote, the neighbor, right? You will see all the information that you can look at that for your reference, okay? Now, this is for what concern, you can use this, right? This configuration for leaf to spine and spine to core, right? Question? How does the spine? How does the spine discover the IP address of the leaf? I mean, it doesn't need to because I just say remote AS external, right? And then based on the... Well, that's negotiated through BGP, right? So they exchange, this is the local AS I have. Yeah. Well, it's based on what, how do you know the peer autonomous system? Is based on the control plane protocol that I receive on the link from my peer. It will contain his number, right? I will send you mine, you will send me yours, and we'll basically establish the peering based on that. We can discuss more offline if you want here at the end, and I can actually, if you want, I show you how it works in detail. Okay. This was basically leaf spine, spine core. Now, as I said, modern data center, you also need to do peering with the host, right? And again, this we make the example of a Kubernetes node. Kubernetes node also peer BGP with the fabric. We want to ensure that also that configuration or that peering between the leaf interface and the Kubi node, it's automated, right? And so the configuration here will be similar on the leaf side. On the Kubi side depends on what you're running, right? This could be Calico, could be FRR, it doesn't matter. The point is that the peering with the leaf will automatically come up, and it depends on how that node is interconnected, right? If it's interconnected with a single attached host, as a single attached host, you can use the link local address to build this peering, like I showed you in the previous slide between two network nodes. And then behind that, there will be an IPv6 global address that the Kubernetes node use, and this is basically to register with the Kubernetes controller, etc. Right? That's the identity of the node itself. But it uses basically, it is advertised, this purple address is advertised into the network using that BGP peering that I do LLA to LLA, using the LLA to LLA peering. If you attach the host with a more traditional VPC, we can still peer layer 3, and you know better than me, we support peering layer 3 over VPC. At that point, you need SVIs on the leaf, right? And you will have an SVI with an IP address here with a link local address, and an SVI with a different link local address on the other box. And you will establish two BGP peering between the Kubi node and the two leaf. And again, then use this peering to advertise the IPv6 node address and also the pod address, the service address that this Kubi node hosts, okay? What we cannot do today, because some people look at this as like, well, yeah, this works, but I really like having a fully routed a fully routed deployment. And here you bring back VPC, which smells and feels more like a layer 2 still construct. Well, it would be nice if we could peer L3 between the two interfaces without requiring VPC at all, right? This is working in progress because there is some. And I'll be honest, it's also this part is a bit out of my depth because I'm not a Kubernetes expert of any sort, but essentially what this does, I need to be able to bring up this peering to then advertise the purple node, and there is a catch-22 situation. There is some some works that needs to be done on the Linux kernel for this to work, right? And this is working in progress. Once this is completed, then you will be able to do two layer 3 v6 peering, using the two separate interfaces and use that to advertise, right? So it's two peering like it is here, but instead of peering with SVIs, you will really peer with layer 3 interfaces on the leaf side. That's the main difference, right? It's a purely routed infrastructure at that point, end-to-end from the server to the other server, okay? That's the main difference. There is no more L2 construct in the middle. Now this is a bit heavy. Last thing I want to cover. Concept is simple. The slide is very rich because then you'll bring it home and you'll study it. Lucas made the slide, right? I'll give you just the simple gist of what this is about, right? Again, same scenario. I'm building my Kubernetes cloud-native application and I want to provide connectivity to this. Now, if I take this example and I have 1, 2, 3, 4, 5 nodes. In this example, these 5 nodes host the same service, right? What does it mean? It means that the same subnet that in this case is a v6 address, this FC001 1/128 is going to be advertised by each node to each leaf using the BGP peering that we saw in the previous slide, right? So these two nodes send it to leaf 1. This node 3 sends it to leaf 2 and 3 normally, right? By default, what is going to happen? By default, when the leaf receives this information and re-advertise the information into the fabric, what is the leaf going to do? The leaf is going to change the next hop address to itself, right? It's like, okay, fabric, if you want to reach this service, send the packet to me because I received that information from locally attached or locally peering entities, so I know how to get to that. So send the packet to me. The end result of that, if you go on the spine, is that to get to that service, right, this service here, which is hosted by all 5 nodes, I will basically have 3 paths, right? 3 paths via the leaf 1, via the leaf 3, and via the leaf 5. Because these are the leaves that told the fabric, I know how to get to that address. Is there something wrong in doing that? There is nothing wrong in doing that. And this shows you how the load balancing, if I have something connected to leaf 6 that needs to talk to this service, I will have 33% of the traffic going here, the other 33 going here, the other 33 going here, right? ECMP decision made by the source leaf. Is anything wrong in doing that? There is nothing wrong in doing that, but think about if in Rack 1 I had 10 nodes providing this service. Do I really want to send to 10 nodes 33% of the traffic, and to the other rack where I have only 1 node offering that service, 33% of the traffic? It seems a little unfair, right? I have all these nodes that can provide my service, and I only give them 1/3 of the traffic, like the rack where I have a single node. That poor thing now needs to work for 10. What would be nicer is, instead, if we could maintain inside the fabric the information about the node itself that offers that service, okay? And in order to do that, we want to basically get to a per node next hop behavior. How do we get to the per node next hop behavior? And here I'm talking again routed fabric. I want to be clear, we have an equivalent functionality with VXLAN and VPN. They leverage a configuration knob called Export Gateway IP. If you're interested in that, find me at the end and we can talk about that, but it is essentially the same concept. Per node next hop means when leaf 1 gets the update from node 1 and node 2 about this prefix, instead of advertising inside the BGP toward the spine in BGP with itself as a next hop, which is the normal BGP behavior, the default BGP behavior when you have eBGP peering, it will basically advertise, it will keep the next hop information that is the original next hop that originated the prefix. Next hop and change, right? It's a BGP next hop and change configuration knob. So this leaf will advertise that these prefixes is as a next hop node 1, node 2. This leaf 3 will say next hop is node 3. This leaf 5 will say next hop is node 4 and node 5. There is a second knob that the leaf needs to enable for that to be possible, which is called add path, BGP add path. So I need to be able to advertise 2 times the same prefix because the prefix is the same, right? Even if I receive it from 2 different nodes, I advertise it twice with individual next hop. What's the result of that? The result of that, if I look at the spine, is that now to get to the next hop, I have as many, to get to the service, sorry, I have as many next hop as there are the number of nodes that host or offer that service. And this is good because if I go here and look how the traffic is now distributed, now I have 2 flows go to rack 1 because I have 2 nodes offering the service. 1 flow goes to rack 2 because I have 1 node offering that service, and 2 flow go to rack 3 because I have 2 nodes offering that service. If I add 3 more nodes in rack 1 offering the same service, all of a sudden it will become 5, 6, 7, 8 path, and 5 of 8 amount of traffic will be sent to rack 1 because I have more compute power there that offer the same service, right? Now, the BGP information inside the network reflects the compute power of what is attached to the different leaf. Do you see the difference between the two? It's useful, right? And it's useful for BGP, routed, and is useful for if you use VXLAN VPN. As a side note, I just finished writing a paper about service integration with VXLAN VPN. We use the same concept when a firewall advertises prefixes, a firewall connected to the fabric for different use cases, but we use the same technology. Basically keeping the original information about the node that advertises a service instead of having the leaf hiding that from the perspective of the rest of the fabric. Okay? So I wanted to cover also this because it's nothing new, again, but it's something that could be very useful and very easy to tune if you build a routed fabric or a VXLAN VPN fabric. Conclusion, very easy, 4 minutes for conclusion. Conclusion number 1, based on the discussion, the architectural discussion we had, we can scale from a very small network to a very large network. I gave you, hopefully, some ideas how you can do that. You don't need to start with already the forecast in mind of how big you need your network to be. You can start small, and you can add more blocks as the need arise. Grow, pay as you go, scale as you go. Number 1. Number 2, bigger is not always better. Some people may disagree, some people may agree. Use fixed form factor switches instead of modular. And I gave you some food for thought why fixed is better than modular nowadays. But if you like modular, we like you as well, right? Because we have both. Okay? Key takeaway number 3, more switches not necessarily means higher cost. I'm a technical guy. I hate going to the discussion. I don't pay anything for my switches, so it's like it's easier for me. But Lucas went through actually excruciating detail, and I think you have it in the hidden slide about the math, right? Not always replacing the modular chassis with more non-modular switches, right? Not only saves you power and cooling, but also from a cost of the switching perspective, if you do the overall math, the cost will go down. Now, obviously, I know what you're thinking. There is also, you show me lots of connection. There are optics that come into the picture. Lucas included also the calculation of the optics cost, right, when he came with this key takeaway. If you disagree, go find him and kick his butt. And the last thing, routed fabrics are a real thing, right? They exist. We fully support them. More importantly, we have work on functionality for routed fabric for a long time, and we brought it back now into an XOS, as I said, this BGP auto fabric in 10.2.3, to reflect the new reality where we may want to give the capability to application owners to connect stuff to fabric and bring up the fabric in a more plug and play way. Okay, so that's where BGP auto fabric comes into the picture. There are some resources for BGP Auto Fabric, as you see here, support is starting 10.2.3, 5549. By the way, 5549 now is called 8950, evolves, but is essentially the same thing, and 7938 is the building eBGP-based routed fabric that I mentioned before. Last very thing, this is the last time I present this session because I won't present it in Vegas, but, so, even if you give me all once, it's not they're going to take the session for me because I don't have it anymore. But it will be good, since I need to pass the baton to another TME, give us some feedback about the session. What you like, what you didn't like, right? Because we want to be sure that we'll be rerun again, and we want to be sure that we give you more valuable content if you come back, or valuable content to new people that may come. And more importantly, look at this. How can you stay without this? And also, last year, we gave you socks. This year, we give you the T-shirt. Next year, we give you the underwear. And then you will have the full set available. Okay? Thank you for coming. Enjoy the rest of the show.